So this is week 2 of Intelligent Agents, and we're just gonna try something different this week. Um, I have here my friend Izzy, and I'm basically gonna go through what I learned with him, and if he has any questions or anything or comments, he'll share it. It's more of like a podcast kind of setting. Thank you. So just a recap of the last um, week. What are neural networks? Are you familiar with neural networks?
I've heard of the name neural network, but I don't think I've learned what they are.
Well, it's it's a type of machine learning model, right? Or it falls underneath machine learning. So it's actually different because it's the way it like learns, right? So this is a review. So basically, these neurons, right? Each of them contain like activation. So you can think of it like a human brain. Each of these neurons contain like a data for input data, right? So if we're trying to distinguish, what's it called, like digits, right? This would hold information like pixels to that, right? To recognize digits. So each of these A values over here are activation neurons, right? And these W's are weights, right? So continuing, yep. So every neural network, or when doing neural networks, we have a bias and weights. So it's kind of like when we hear machine learning, like when we adjust stuff, like like adjusting the weights and everything like that. Um, this is what they're talking about. So we adjust the weights and everything, so we can adjust which neurons are activated, right? Because when it comes to neurons, right, going to the next slide, each layer is associated with like a particular type of thing we're trying to determine. So like for instance, one layer is like this is the input layer. This layer would be trying to detect like the edges, right, the top edge of the nine, and then another layer would be like this line right here, right? And we adjust these weights so only certain neurons activate, right? So we get more of a closer like approximation. So how is the machine learning, right? It's technically just finding a minimum, right? So like the lowest point in the graph, and this is going to be important. Yeah. So yeah, I was just saying there's weights and bias, right? So like when it comes to when it comes to neural networks, right? It's like we have weights and bias, but how do we determine what's the best fit for it, right? And that's where the cost function comes in, right? So the cost function basically is like it it determines what is the cost of the error of the output, right? So let's say we're trying to detect this three, um, we have to determine what like the I guess difference, the error in our calculation, right? So it's just a measure. A cost function is just a measurement of how well the neural network's performing. It quantifies the difference between the network's output and desired output, right? Yeah. Any questions? Not yet. Okay. So this is what it looks like. So each neuron, we calculate the difference, and we take the square of that, right? So, um, I'll explain it right here. So like our value desired, right, it would be 1, but the actual value is 0.2, and we take that difference and then square it, which we get 0.64, right? And the smaller the cost is, right, meaning the error, the better, right? But the larger, it's more wrong. Does that make sense?
Yeah. How do you minimize cost?
Well, we'll get there. So basically, we take all these averages of these squared errors, and this output is the cost function. So it takes all these weights and biases, right? And then outputs one number, which is the cost. And this number tells us how, like, basically how our neural network's behaving. So if it's bad, it's good. This number will determine that. So you asked like how do we like adjust these, right? It's a thing we call with gradient descent, but this is an introduction to it. So we want to improve the neural network, and the way we improve that is through adjusting the weights and the biases, right? Because the neurons are like set values, right? But it's which ones we want to activate to get the desired output, right?
Yeah.
So like this is our cost function, and it usually takes the weights and biases, right? But you could think of it as like a single input right here, right? So think about it this way. Like remember how I said we were trying to minimize the um, we want the smallest error, right? And the way we do that is just by taking the derivative and finding the the minimum, right? But sometimes it's not feasible for complicated like functions, right? So what we do is that we take steps to find a local minima, right? Because trying to find like a global minima is complicated, right? So we take some arbitrary point where we start off, and then we find the slope. So you would take the derivative where you're at, and depending if it's negative or positive, we shift left or right, right? And we do this at each step. So we're taking small steps, right, until we can find the local. In this case, like since it's positive, we want to go left. That means that it's going up, right? We want to go down. Does that make sense? So if the slope is, for instance, for this point right here, if it's negative, the slope here is negative, right? That means we want to keep going to the right. Does that make sense? Until we reach this local minima. Yeah. So, like, as I was saying earlier, like, there's different points where we can get this local minima, right? It depends entirely where the input starts. So if we start right here, it would fall eventually right here. If we were to start right here, it would choose this one, right? It's whatever's closest to it. So trying to find a global minimum is crazy hard, but finding a local one is easier, right? And as we get closer to the bottom, the steps become smaller, so we know we're approaching a minimum, right? And then when we reach the bottom, how do we know we reached like a local minimum? It's when the derivative is zero, right? Because there's no change in like the slope.
Okay.
Yeah, right. It sounds like similar to like math, right? You take calculus.
There's a lot of math.
Yeah. So now, like, how this is applied to cost functions? Well, you could think of like our x and y's as our inputs, right? And then the z-axis is the cost function, right? So, like, this is actually a math equation or function. It's called gradient. It's a gradient function, right? And it basically just calculates the direction of the steepest ascent. So we're taking the concepts of what we're talking about here, but applying it in a 3D plane. Does that make sense? So how do we compute, the gradient descent? So first we take, the gradient descent, and then we take the small step towards the bottom, and keep repeating until we reach a local minimum. So this is just for like a 3D plane. Does that make sense? So now we're answering the question about weights and biases. How do we adjust them to find the best, it's by using this gradient function. So we're trying to minimize these error values by putting it down or adjusting them. Oh yeah, the meat and potatoes of gradient descent. So, like, sometimes one neuron weight matters than another. So sometimes we just want, the one that gives the most change, right?
As long as it just has like one A and one B. One A after. Oh.
Yeah, so basically the cost function, the gradient descent, helps us determine what we should prioritize, right? And it's basically just like vectors. So like for this instance, you could tell this vector 3 and 1. This one has more of an impact than 3, right? So if we apply 3 over here to this weight, we know this is going to change more than the one that's applied to this. And you can think of x and the x squared and y squared as different neurons. Does that make sense? So since we apply the weight of 3, it's more impactful than applying the weight of 1 to this one. There's more of a change in the direction. So yeah, that's basically it. So like, and then goes into like this guy named Demis Hassabis. He was just interested in chess, and like every intro to machine learning class is like they always mention chess. because it's like, oh, what if we can create a bot that plays against it and learn like the moves and stuff like that. So of course this guy got interested in programming and computer science, which led an interest to programming AI, and there was a massive breakthrough with Go. So they made a bot called AlphaGo, and Go is just a complex game with 10 to 170. Yeah. So basically, AlphaGo was this bot that beat this world champion, and then the way it worked was using neural network models. So it was such a breakthrough. So he goes into proteins. It's basically the essential building blocks. It's like some biology stuff, and the 3D structure of a protein determines its function, right? So kind of similar to like trying to predict a digit, or to AlphaGo. The problem here was trying to like predict the amino acid sequence, right? So the protein folding problem aims to predict a protein's 3D structure, right? So they basically made a competition out of this, and people started using machine learning, which created AlphaFold 1, and then they improved it to AlphaFold 2, and now we have AlphaFold 3, which is the latest version of AlphaFold. And it's basically interaction between proteins and molecules. So
My brother does research on that.
yeah. So it's just important because this plays into computational biology. So you could think of it where biology and computer science intersect, and this is kind of important because like it can accelerate drug discovery.
Nice. That's really cool.
Yeah. Thank you for joining me today.
Yeah, it was a pleasure.
Yeah.